Okay, let me share my screen. Okay. So the second topic that we have covered last week, this is the second, is already the improper integral. And we have discussed under improper integrals two types. So when we speak of improper integrals, they are the integrals that the properties that were covered in the definite integral will not be 100% applicable. In the sense that in this type of integrals, we have a function having a discontinuity on the designated interval, which at the same time also represents the limit of the integral. And we have limits of integrals here, which are either infinite or both of the limits being infinite. So based on what we have covered last meeting, so we discussed type 1, wherein the limits of integration or a limit of integration is infinite. So you have this example here, wherein the upper limit is infinite. The lower limit is a real number. Under type 2, the limits are not anymore infinite. So you can see that both limits are real numbers. They are not real numbers in nature. But if you're going to plot your function on this designated interval, which also represents the limit of your integration or limits of your integration, your function will have a discontinuity, or shall we say an infinite discontinuity. And this is actually what we're going to discuss this afternoon. The function that has an infinite discontinuity on the designated interval. But to review on type 1, so we have three cases under this. Under case 1, or type 1a or case 1a, we have the upper limit as infinite. Under type 2 or case 2, we have the lower limit as negative infinity. And the third type is when both limits are all infinite. So we have discussed this. So let's go to the first type. So as an example of the first type and the second type, and the same thing with both types being having the intervals which are infinity. Before I proceed to that, we also discussed the concept of the convergent and the divergent functions. So when you speak of convergent, if you're going to evaluate the integral using the concept of the limit will exist, meaning your answer will be any real number. And if the answer of such a limit is a real number, then the integral is said to be, or the improper integral is said to be convergent. Otherwise, if the limit does not exist, so when do we say that the limit does not exist? Of course, when the answer is infinity or negative infinity. So if the limit does not exist, we say that the integral or the improper integral specifically is divergent. Okay? So this concept of convergence and divergence could be applied rather one at a time to any of the cases that was discussed in here. Okay? So not both, but only one at a time. So meaning if it's convergent, it cannot be divergent anymore. So if it's divergent, it cannot be convergent anymore. Okay, so let's go to the improper integral case 1a. The upper limit is infinite, so we have discussed that. And the example that was used here is in the case of the function, which is 1 over x squared, which is to be integrated from 1 to infinity. And since what we do with integrals having infinite limit is that we replace the infinite limit with a variable and then evaluate the integral of that particular function as that same variable, which we use as a replacement approaching infinity, this is how it's going to be. Okay, represented in here. So you have 1 to t, where t here approaches infinity. So what was done to the function 1 over x squared actually was integrated. So if you're going to integrate 1 over x squared from 1 to t, this is the answer. Because the answer of this integral here is negative 1 over x. And if you substitute the limit 1 to t, you will have 1 minus 1 over t. So to finish the evaluation of the improper integral, which is originally from 1 to infinity, you will evaluate the limit of this as t approaches infinity, as you could see in here. So if we substitute the limit of, or rather if we evaluate the limit of 1 minus 1 over t as t approaches infinity, the answer is 1. And as such, the original integral that was given, let's go back here. The original integral that was given, which is 1 over x squared dx integrated from 1 to infinity, which is to be evaluated as the limit of the integral of 1 over x squared dx from 1 to t as t approaches infinity, is equal to 1. Okay? The graphical interpretation of this limit of the integral applied on this improper integral is actually illustrated in here for the same function in 4 different conditions wherein we substituted the value of 2, 3, 5 to t. So if we substitute t, which is 2, this would be 1. Remember, our answer is 1 minus 1 over t. So if we substitute a t, which is 2, that would be 1 minus 1 half. So your answer is 1 half. If t is 3, you have 1 minus 1 third, so that would be 2 thirds. If t is 5, that would be 1 minus 1 fifth, and the answer would be 4 fifths. If t is infinity, that would be 1 minus 1 over infinity, which is 0, and the answer is 1. As such, we say that this improper integral evaluated in this manner has a value or has an integral value equal to 1. And this one is an example of case 1. So as such, it's placed in here case 1A or type 1A. This is case A under type 1 wherein the upper limit of integration is infinity. Okay, so we evaluate the integral as its limit approaches the value in which the upper limit of the integral approaching infinity. Okay, amo ni siya ang ating discuss last meeting. Now, under case 2, so this is the other one, you have infinity, or you have 1 over, or rather 1 to infinity of 1 over x dx, wherein you are to tell whether this would be convergent or divergent. So this is an example under case 1 as well, because your upper limit here is infinity. So this time, in this example, we determine whether the integral will be convergent or divergent. Now, we move forward. So if you're going to evaluate the limit, or rather the integral of this, the answer, of course, based on what you have learned, is ln. So ln of x. However, we evaluate this improper integral as a limit as t approaches infinity, where t here is the variable, we replace the original upper limit, which is infinite. So you have now the limit of ln of x as t approaches infinity. Now, what do we do? Since if we substitute here the upper limit t and the lower limit 1, this would be our answer. And this ln of 1 will be equal to 0. Okay, the ln of 1 that you have here, this one is equal to 0. So that leaves us with the limit of ln of t. If we substitute infinity to the t, the ln of infinity is infinity. And since it is infinity, we say that the integral does not exist. So since it does not exist, or the limit of the integral does not exist as a finite number, so we say our function or our integral is said to be divergent. So that's how we apply the concept of convergence and divergence to improper integral. If your answer here would have been a real number, then the integral is said to be convergent. Okay, so we're still discussing the example of case A under type 1. Now we go to case B. This time it's the lower limit that is negative infinity. So from negative infinity to b. Now again, I will emphasize that we mean with negative infinity as infinitesimally small value. If it's positive infinity in the upper limit, it's infinitesimally large value. Now, if you evaluate this improper integral, it would be interpreted as this. So we replace the infinity here, or specifically the negative infinity, by t. Then evaluate the limit of this integral as t approaches infinity. Okay, so this is under case 2. So as for an example here, let's say you have this one. Now, negative infinity to 0. And based on the techniques of integrals that were discussed, this could only be evaluated using integration by parts. So you will need to evaluate this one using integration by parts, replacing the negative infinity in the lower limit as t or by t, and then evaluate the resulting integral here after substitution of from t to 0 in terms of a limit where t approaches negative infinity. So first thing you need to evaluate, then substitute the limits, then evaluate the limit in here. Now, we proceed. So under this one, if you're going to use by parts, so we integrate by parts. And your answer is x e raised to x minus the integral of e raised to x dx. For this particular integral, now in the first term, you will have x e raised to x. And in the second term, if you will evaluate this, that would be e raised to x. This one, right? And your limit for this integral is from t to 0. Now, if you're going to substitute 0 first, because it's the upper limit, this will be 0. And this would be minus e raised to 0. That is why you have here negative 1. Anything raised to 0 is 1. And then if you substitute the lower limit, t, for all the x's here, so you'll have minus t e raised to t minus minus, so that would be plus e raised to t. Substitute here t for the x. So this is now your answer. But of course, we're not yet done because this is just but your integral in which you have substituted the limit. You have not yet evaluated the limit of this as t approaches infinity. And that will be covered here on the next slide, as discussed also last meeting. So we know that e raised to t approaches 0 as t approaches negative infinity. So if you go back to our original answer, if you substitute here e raised to infinity, your answer for the first term would be minus infinity e raised to infinity minus 1 plus e raised to infinity. Now, this is the part where I discussed also that in your math differential calculus, yung EMA 101, this is the indeterminate form. Meaning, the answer is not acceptable for now because infinity times e raised to infinity, which is infinity, is indeterminate. So that is why in the next slide, there's a mention of it being processed using L'Hopital's rule. So we need to process t e raised to t by L'Hopital's rule. L'Hopital's rule is only applicable for rational expression. When we speak of rational, it's a fraction. So what happened here is that we rewrite the e raised to t as an e raised to minus t in the denominator. Because anyhow, this t over e raised to minus t is just equivalent to this. Then we evaluate this particular expression as t approaches negative infinity. Now, if you do that, this will be still negative infinity if you substitute infinity there. And this would be e raised to, that would be negative, 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 that would be positive. And your answer here will be infinity over infinity. This is another indeterminate form in your differential calculus. So L'Hopital's rule suggests that whenever you have indeterminate forms in rational form, you can differentiate separately the numerator and the denominator. So if you differentiate it, the answer of this differentiated in terms of t is 1. If this is differentiated, of course, that would be EU du. The derivative of negative t is negative 1. So this is now the answer after you have differentiated. Now, if you substitute the same value in which t approaches 2, you will have, in this case then, you will have here 1 over negative e raised to negative, that would be positive. And this one is 1 over e raised to infinity is infinity. And this would be 0. 1 over infinity or 1 over negative infinity is still 0. So that is why you have here 0. So in the first answer, in the first term rather, here in the answer you will have 0. So if you now substitute values here, you will have 0 minus 1, and this one would be e raised to infinity. E raised to infinity is infinity. So this is infinity. The answer to this is infinity. So let's proceed. So that being 0, so if you have here, you have, negative infinity. Sorry class, we are to substitute negative infinity here, not positive infinity. So this will be 0. E as raised to negative infinity. I forgot, I said infinity here, it's negative infinity. So this would be 0. E raised to positive infinity is infinity. Okay, so if we substitute the values that we have minus 0, minus 1, plus 0. So the answer is negative 1. Since your answer is a real number, then we say that the integral is convergent. Okay, it's convergent because the answer is negative 1. So I'm sure you have listened to this recording already. Do you still have any questions in this part? Okay, so I'm just reviewing. So we go to the last example here under case C, type 1, case C. Both limits are already infinite, so negative infinity and positive infinity. So it's suggested that you will evaluate this improper integral by using the sum of two separate integrals wherein the lower limit and the upper limits are negative infinity and infinity. To make things simple, it is suggested as well that for this A or for any letter that you have chosen in between negative infinity and positive, it is suggested that you make this 0. That way it would be easy to substitute later on than compared to other real numbers. Anyhow, this A here, or any letter that you want to place for A in here in lieu of A, should be a value that is between a negative, a very small number, an infinitesimally small number, and an infinitesimally large number, which is infinity. So 0 is in between. So you're not violating any rule with that. Okay? As is stated here, any real number can be used for A. Actually, the letter A is also arbitrary. You can choose any letter that you want for the A, as long as it's between, or this value is between negative infinity and positive infinity. So what we do in here, for this specific example, we separate it into two integrals and take the sum of the two. So we start with negative infinity to 0. And then since we use 0 here, that would be our lower limit here. If this is 1, this should also be 1. If this is 100, this should also be 100. If this is negative 10, this should be negative 10. Okay, so this 0 is just arbitrarily chosen. So you just copy your functions and you have now two improper integrals here to evaluate so that you'll be able to find the value of this third case under type 1. Now, this is what we did. So we evaluate this. That's an arctan of x. This one also is an arctan of x. Now then next is you substitute the limit t and 0. So t for the upper limit and 0 for the lower limit. You substitute it to your answer. Now, what would be the answer to this arctan of, you have here infinity. So you think of an angle wherein the tangent will be an error if you process in your calculator. That angle is actually 90 degrees. So that's your pi over 2. Whereas if we say we find the tangent, or rather the arctan of 0, or an angle whose tangent is 0, that would be also 0. In this case, this is 0. If you check in your calculator, tangent of 0 is 0. So the arctan here, the angle whose tangent is 0 is 0. Leaving us with a single term in here, which is the limit of the arctan of t as t approaches infinity. So again, think of an angle whose tangent will be infinity. And that will be 90 degrees. Now the same thing in here. You substitute the limits 0 and t. This time 0 is the upper limit and t is the lower limit. This time this one will also be 0, leaving us the limit of negative arctan of t as t approaches negative infinity. What particular angle will yield a tangent that is negative infinity? Meaning you're dividing it by a negative number. And that angle is negative 90 degrees. Remember, tangent is opposite over the adjacent. So if it's opposite over the adjacent, what particular angle will it be? That will give you tangent which is 0, but the opposite side is negative. So, as a review again, based on what you have learned in your trigonometry, if you do clockwise measurement in direction, this is positive 90 degrees. This is positive 90 degrees. Opposite is 0, adjacent is 1 or any number. So that would be still 0. So that's 90 degrees. Whereas this one, your opposite side here is negative. This one is positive. So negative over any value, that would be negative. So that is why you have negative infinity here for this one. You place here arctan of negative infinity. What angle will yield a tangent which is negative infinity? That would be the negative pi over 2 here, or the negative 90 degrees. So this is minus. So negative of negative, that would be positive. So these two separate integrals now will be added, or they were added, to give us the answer to the original. So this is the original. So we get the value of this and this from here. They're both pi over 2. So the answer to this improper integral under type 1 case C or case 3 is pi. You add pi over 2 plus pi over 2. Now these 3 constitutes type 1. So all these 3 cases is under type 1. The limit or limits of integration are infinite. Okay? Any questions so far here? Anyway, this is just but a review of what we've discussed last meeting before I go to type 2. There's none? Sige. So we will continue then under type 2. So we're now going into discontinuous integrals. That's said to be type 2. We say they are discontinuous because the function itself, if plotted on the designated interval, which is at the same time also the limits of integration, it will not be a continuous plot of the function. There will be an infinite discontinuity on the graph of the function. And as such, it's still categorized under improper integral. Because if you recall class under properties of integral, the value of a particular definite integral will only exist if on the designated interval your function should not have any infinite discontinuity, or it should not be discontinuous on the designated interval. For this one, in which we have under improper integral, it is discontinuous. And as such, as I've said a while ago, not all the properties under definite integral is applicable for these improper integrals. Okay? Now, let's go to now set type 2 since we don't have any questions under type 1. So let S be the unbounded region under the graph of the function f and above the x-axis between a and b. For type 1 integrals, the regions extended indefinitely in a horizontal direction. If you notice, class, in type 1, our graph of the function can either be infinitely increasing in area towards the right or infinitely increasing in area towards the left, part of our Cartesian plane. So it's going to only either to extend to the right or to the left. As stated here, it's extended indefinitely in specifically horizontal direction. The manner in which the area of the curve extends, it's horizontal, either to the left or right. Now here the region is infinite in vertical direction. Now this one is referring already, this infinite extension of your area in the vertical direction is referring to type 2 because ang horizontal direction is for type 1. Okay? The area under the curve is extending infinitely either upwards, in this case, or downwards. Now, let's look into this particular case then specifically. Okay, we'll have this one. Just scroll class. Okay, so we're now on slide 25. I will project this so this will appear bigger in your end. So just let me know if it's not projecting. Suppose f is a positive continuous function defined on the interval a to b, but has a vertical asymptote at b. The area of the part of S between a to t, this one, the shaded region is, so look at this, the area of the curve f of x is extending infinitely in this direction upwards. Now, it's not extending infinitely to the right or to the left, but in this case, it's going to extend infinitely upwards. Okay, it's not projecting this. Okay, I'll go back. Thank you, Eugene. Okay, let me check again. I'll project again, class. Let me know if it is projecting. I want a bigger space to write on. Is it projecting? Still not projecting. Okay. So I'll try to make it bigger. This part here. Okay. I think that will be bigger now. Now, the limit of integration, class, or the limits of integration for this function of x is from a to t, as you could see. Now, if you notice, as this particular function approaches the line x equal to b, it's going to extend infinitely upwards. Going to approach, for this curve here, I'm going to write a blue line first. If I'm going to extend this line x equal to b in here upwards, that would be it. That goes the same way here downwards. Now, this curve is going to approach this line, class, or this vertical line infinitely, asymptotically, meaning it will never cross this line. but it's going to be asymptotic to the line x equal to b. And as such, we say that this area under the function of x, y equal to f of x, is extending infinitely upwards. It is being asymptotic to this vertical line x equal to a, or rather x equal to b, where b is this line in here. And we say that this particular function has an infinite discontinuity as t approaches the value of b. So the graph of the function is infinitesimally going upwards, at the same time being asymptotic to this line x equal to b. This falls under type 2. Type 2, which is the curve of your function having an infinite discontinuity on the designated interval. In this case, class, the designated interval is from a to b. So a is not infinite, b is not infinite, so it cannot be categorized under type 1, wherein any or both limits of integration is infinite. Okay? Now I will clear my markings here and proceed to the next slide. So if it happens that a of t approaches a definite number a as t approaches b from the left, why am I saying from the left? If you see, class, a negative sign here, this means that this value b is approached from the left side. If it's b raised to a positive sign, meaning this value b is approached from the right side. I hope this was also discussed in your differential calculus because it's being covered here. A negative sign or a positive sign as a superscript or as an exponent in any value in which a particular value variable approaches to represents from which direction in the Cartesian plane is it coming from. So the negative here means it's being approached from the left side. I'll go back to our curve so you will see. Okay, my markings first. So this x equal to b line is being approached from the left. See, this one is from the left. If it's being approached from the right, it should be coming here. Sorry. It's like if I'll have another one here, it should be approached from this side. Sample lang, class. That. So then this would be b plus. It's this b line, this x equal to b line is approached from the right. This one is approached from the left, as you can see here. The curve is from the left side going up. Okay, so that's the meaning of the positive and negative exponent. So let's go to that slide. So if it happens that a of t approaches a definite number a as t approaches b from the left, then we say that the area of the region S is A, and we write that the integral of the function integrated from A to B is equal to the integral of that same function integrated from A to T as T approaches B, the value B, from the left. Use the equation to define an improper integral of type 2 even when f is not a positive function. So whether this function, by the way, class, is negative, it doesn't matter. No matter what type of discontinuity f has at b. So whether this is negative or positive, this is still our notation for a type 2 type of improper integral wherein the function has an infinite discontinuity. Okay, interrupt me if you cannot follow. I will proceed to the next slide. So now we go to improper integral of type 2. The function has an infinite discontinuity, and we also have here case A. So this is case 2A, type 2 case A. So if the function is continuous on the interval A to B, you see this class of a parenthesis. If it's a parenthesis class, meaning B is not included in this interval. If you have a bracket, it's a closed interval. If you have a parenthesis, it's an open interval. So it's discussed in differential calculus that if you have a bracket for a particular value, meaning that value is included in the designated interval. Whereas if you have a parenthesis, it's an open interval, meaning this value of B is being approached to but not included in the interval. So closed interval for A, open interval for B. Okay? So if F is continuous on the interval A to B and is discontinuous at B, then this is how it is to be evaluated. So that's the example that we started off. If this limit exists as a finite number, this is how its curve going to look like. The function, the line x equal to b, in which t is going to approach to from the left. You have here from the left side. Okay, another one is from the right. So you will be able to distinguish between the two. If f is continuous on the interval a to b, where a this time is not included but b is, then the limit is from t, look at it, from t to b of that particular function evaluated as t approaches a. Now this time notice the positive sign here. The x equal to a line is being approached from the right. We're coming from the right here. And the curve is asymptotic to the line x equal to a, approaching it from the right side. So this time, it's the upper limit that is specified, included in the interval. The lower limit is just being approached to, but not included. In the first one, it is the lower limit that is included in the interval, and the upper limit is the value that is being approached to. So this is approach from the left, explains here why t approaches b raised to a negative sign. And this one is t approaching a from the right because a is raised to a positive sign. So this is case 2b. In any of these cases, what is common is that they have an infinite discontinuity on the designated interval, which is being approached to but never equal to. It's not included. So diri siya naga-infinito, infinitely extending upwards for the line x equal to b. Same thing here, infinitely extending upwards for the line x equal to a. So this is for case A and B under type 2. Do you get it? Can you distinguish now case A from case B under type 2? They have one thing in common. They have both infinite discontinuities on the designated interval. What distinguishes one from the other is how the limits are being approached to and which limit is included in the interval. You have any questions? Okay, so your silence means yes. I hope you'll raise your concerns if you have any as we go along. Okay, I'll proceed to the next slide. Now, the improper integral of the function a to b is called convergent if the corresponding limit exists, and it is said to be divergent if the limit does not exist. So meaning class, the concept of convergence and divergence we applied for improper integrals under type 1, where any or both of the limits of integration is infinite, is also applicable in type 2. So it's still convergent if the limit exists, it's divergent if it's not. Okay, so we're going to apply the concept again as we process the examples that follows here. Any question? Okay, then let me proceed. So now we go to the improper integrals of type 2. Let's see which part does this belong. Is this case A, where you have an infinite discontinuity approach from the left? Case B, if it's approach from the right. Okay, so you have here second x dx to be integrated from 0 to pi over 2. There's a question. Round out daw sila. It's okay. Thank you. Thank you. So you have 0 to pi over 2 of second x dx. Now, you are required to determine whether this converges or diverges. Now, if you look at it, class, look at it, never will it cross your mind that this is improper. Actually, what you're going to do when you see this, you will simply use your calculator and just encode second x dx and then the corresponding limits and give me the answer. But actually, this is an improper integral. Under case 2, because under case 1, or rather under type 2, because under type 1, any of this should be infinite or both. But in this case, this looks like an ordinary integral where all the properties that applies for a definite integral would be applicable too. So let's check why this is now improper. So note that the given integral is improper because, if you look at it, the limit of the second of x as x approaches the value of 90 degrees, meaning if you substitute here 90 degrees for the second, the value is infinity. What is second? That's the inverse of cosine, right? The inverse of cosine. So what particular value or what particular angle will give you an infinite for the inverse of its cosine? That particular angle is 90 degrees. Or other way around, if you take the cosine of 90 degrees, what's the answer? Check your calculator. What's the cosine of 90 degrees? Cosine of 90 degrees, it's 0, right? Even if you're not going to use your calculator, it's a special angle. It's been taught to you in your trigonometry. So, hampal ko yan, di ba? Cosine. What's the cosine of 90 degrees? It's 0. Then you get the inverse of that. So, 1 over 0, that's infinity. Okay? It's the second. So, the reason why it's an improper integral, because the limit, as we approach the limit of this second, as x approaches 90 degrees from the left side, is infinity. Okay, let me check. Miss, excuse. It's okay. It's okay. Just put in the chat box those who have problems with their internet. It's noted. Thank you, Jim. So this is an improper integral because you have an infinite discontinuity in your function as the limit here 90 degrees is approached to. So from 0 to 90 degrees approach from the left side of the Cartesian plane, the value of the second is infinite. Why is it infinite? Because it's going to extend infinitely upwards. So then the infinitely upwards is positive infinity. So then it's an improper integral. Now, let me proceed to the next slide. This is the computation that way you will see. Okay, why this one is an improper integral. So, second, so we say the limit of the second function from 0 to t. So, we change the pi over 2 here to t. And this t now will be replaced, by the way, class, this should be t. Okay, another typo error. Probably have a lot here because of a lot of things to type. So this should be t. This t here approaches pi over 2 from the left side. This should be t. And this should be also t. What happens is, we just, of course, class, we just integrate this one. As if we're just integrating any ordinary integral. What's the integral of the second? It's the second of x plus tangent x. ln specifically. ln of the second x plus tangent x is the integral of second x. Now we will substitute 0 and t here. So we'll have the ln of secant t plus tangent t. You replace the x by t. And then second is substitute 0. So ln of secant 0 plus tangent 0. And the answer is 1. How do you know that? You just substitute here. So secant of 0 and tangent of 0. What is tangent of 0? Over or opposite over the adjacent. What is tangent of 0? It's 0. What's cosine of 0? That's 1. You can use your calculator. Cosine is secant is 1 over cosine. So that is why I'm saying cosine. Because if you know the cosine, you just have to invert it. That would be already your secant. That's the reason why the answer for the lower limit here, if you substitute 0, is ln of 1. Because for this one, the ln of the secant of 0 is 1. But the tangent is 0. Okay? So you have your ln of 1. Now, after you have evaluated the integral, so what happens is the same as type 1. Evaluate the integral, substitute the limit. So this is what happens if you substitute the limit. But it does not end there. After substituting the limits of integration, you will evaluate the limit of the new variable that you have placed in here in lieu of the value of pi over 2 as t approaches pi over 2. As you approach this 90 degrees. So if you substitute 90 and 90 here, by the way, ln of 0 is just 0. So your answer will be dependent on this. The ln of secant 90 degrees plus tangent of 90 degrees. What's the tangent of 90 degrees? Tangent of 90 degrees. Inalata to nag-istorya sang tangent 90 degrees. What's the tangent of 90 degrees? Salamat. Yung nag-answer. Infinity. The tangent of 90 degrees is infinity. This is already infinity. What's the tangent? What's the tangent? What's the cosine of 90 degrees? Cosine of 90 degrees. 0. So if you have 0 here, 1 over 0 is infinite. Right? Because this is secant. So secant is 1 over cosine. So if you answer that the cosine of 90 degrees is 0, then that would be the cosine of the cosine, or the secant of 0 is infinite. You have 1 over 0, the cosine of, your cosine is 0, so 1 over secant is 1 over 0. So that would be now infinite. Okay? So then you have here an infinite and infinite. So your answer here is infinity. ln of infinity plus infinity, it's infinity. ln of infinity is infinity. This is because the secant of t as t, the secant of t approaching infinity and the tangent of t approaching infinity is as t approaches pi over 2. If you substitute, dali lang gid class. The secant of t is infinity and the tangent of t is infinity as t approaches pi over 2 from the left. So this is correct. Okay? This is not x, but this should be t. So the error is in here because I placed there t. So thus the given improper integral is, says here, divergent. Divergent in the sense that the answer here does not exist. It's infinity. Now, I'll wait for questions or point of clarification. I'm sure this may not be as easy to you, but ask questions if it's not clear. I'll wait for 10 seconds or so for any questions. The process is similar to type 1. Evaluate the integral, substitute the limits of integration, and evaluate the limit as the variable that you change any of your limit here approaches the value that is given in here, it's pi over 2. We change it to t. 0 is never the one that is approached to. Any question? Okay, no question? Okay, so if there aren't any questions, we'll proceed. And clear my markings. Now we go to case 5. So this is still 0 to 1. Just like case 5. Example 5 rather. This one is 0 to pi over 2. This one is 0 to 1 for the ln. If you look at the ln class, right away you will say that this won't be easy because there's no direct answer for the integral of the ln. So you will have to give here, you'll have to use here integration by parts. So you will have to give your skills here and review your knowledge on techniques of integration. So we know that the function ln of x has a vertical asymptote at 0 since ln of x is equal to negative infinity as x is approaching 0, so positive siya from the right. As x is approaching 0 from the right. So ln of x is equal to negative infinity. What does this mean, class? If you will substitute 0 here, just like saying that ln of 0 is negative infinity. Thus, the given integral is improper, and we have, so if this is improper, then we have the original integral replaced by, so it's going to be replaced by this integral. However, you're going to change the 0 value here to t and evaluate the limit of this original integral as t approaches 0 from the right. So, halin naman siya sa right side is i-approach. Now, your function is said to be discontinuous as this particular value is substituted in here. Now, later na lang kung mamangkot. May ipamangkot ko ba later ko na? Let's check if you understand the examples that are given. I'll just finish this one. Okay, so we will evaluate the ln. So, I've mentioned it's going to be by parts. And since ln of x cannot be integrated, it has to be your u. The dv is, of course, the dx. If you're going to integrate the dv and the dx, that would be v equal to x. And, of course, your u will be differentiated to give you dx over x. Now, our formula for by parts is uv minus the integral of v du. Okay, that's our formula. So this is your uv, your u is ln of x, your v is x. So this is it, minus the integral of v du. So your v du, this is your vx, and your du is dx over x. The x's cancel each other, so you'll be left with dx. Now, if you process this, substituting the limits t to 1, you will substitute, of course, 1 first because it's the upper limit. So 1 ln 1 minus t ln t. This one, these two terms is your answer for this. Whereas if this is integrated, this would simply be an x. So you substitute 1 for the upper limit and t for the lower limit for your x. Because this is just x. So you will have to substitute t and 1 for the lower limit and upper limit respectively. Now what happens here is this. So you will have ln of 1. ln of 1, you know, is 0. So 0 times 1 is 0. So you will be left with negative t ln of t minus 1 and minus minus plus t. But this is not yet the end because we still need to evaluate the limit of this as t approaches 0 from the right. Okay? I will clear my markings and proceed here. So you'll have in here, you'll have another problem here because if this is evaluated, right here, this is to be evaluated as the limit of t as t approaches 0 from the right. And you will have here negative t ln of t minus 1 plus t. We don't have any problem with this because this will simply be your constant. It's negative 1, so it's not bothered at all for whatever value is t approaches here. But this one will just be anyhow 0 because you're going to substitute 0 here. So for these two, you have negative 1 because negative 1 plus 0 is negative 1. Our thing here, our challenge is the negative t ln of t. Because in this case, you will have a 0, 0 times ln of 0. Ln of 0 is non-existing. This is infinity. This is infinity. 0 times infinity will be indeterminate. So you have a problem with that. That's the reason why, here my markings here. That's the reason why you have, again, L'Hopital's rule applied to t ln t. So it's, shall I say, I use the term manipulated. The expression t ln of t was manipulated. That way, it will look as a fraction. It would look rational. So ln t is written in the numerator, and in the denominator, you have 1 over t. Okay, this 1 over t, the t will go up. It would look like this. Now, what happens is, since it's already rational, just like the one that was shown to you in the previous example, you differentiate the numerator and the denominator separately. So if you differentiate ln of t, that would be 1 over t, because the derivative of ln is du over u. So what's the derivative of t? 1. What's the u? T. So 1 over t. If you differentiate 1 over t using power rule, this would just be, this is just t raised to negative 1. So you place the negative 1 here and you subtract 1 here. That is why you have here negative 1 over t squared. Now it's already something that we can process. Why am I saying that? I will not anymore write the limit, I will just have this simplified. So if I will simplify this, I will have 1 over t over 1 over t squared. I'll use a different color for you to see. This is negative. I can cancel this one. I still have 1 left here. What happens to this? It goes up, right? That's the one that you see here. It's negative t. This cancels. You still have t in here, so it goes up. The remaining t here goes up in the numerator, and since we have negative here, so it's negative t. So as t approaches 0, the answer is now 0. It's not something indeterminate before we use L'Hopital's rule. That is, before we even wrote it in this portion. If you just simply substituted 0 to t, ln of t, that would be 0 times ln of 0. Okay? So then this would be actually, this would be 0, and this ln of 0 is negative infinity. So you still have indeterminate forms in here. Okay, why do I say it's negative infinity? Because we know that e raised to negative infinity is 0. So if you raise this to e, that would be 0. If you raise this to e raised to negative infinity, these two will be equal now. So it's e raised to negative infinity. That is why you have negative infinity there. Okay? But we're not yet done. We need to substitute to the original answers that we have. But before we do the substitution, do you have any questions? No question? Okay, no question. So we'll proceed. So this is already the answer for the first term. So if we substitute, you have 0. Here, you have negative 1 copied. Then you have 0 for the t. So the answer is negative 1. So this improper integral is said to be convergent because the answer is a real number. The limit of the integral is real number. Noted, noted. Thank you, Cassie. So you have that. Now, what is the graph of the function? This is actually the graph of the function. This is y equal to ln of x. Okay? As this limit of 0 is approached from 1 from the right, so that is why 0 plus, the curve will be extending infinitely downwards. So the curve will be extending infinitely downwards, and this part here will be asymptotic to the line x equal to 0. So again, we go back to the original comparison. Type 1, as for type 1, the curve will extend either to the right or to the left. In the case of type 2, the curve will be extending either upwards or downwards. So that is why it's type 2. The problem, class, with type 2 really is, you don't know it's really improper unless first you look intently on your integral and check whether your answer will be existing for the limit if you substitute that particular limit in your integral. What I mean is this. Unclear. Give my marking slip. Go back to the original. This one. This looks like an ordinary integral. So if you fail to see it as an improper integral under case 2, you will fail to evaluate it properly. What you're going to do, class, is very simple. When you're given integral initially, substitute the value of the limits to the original function. To the original function itself, not to the integral. You substitute L1 here, you will have ln of 1, that's 0. So you have a definite answer. But ln of 0 is negative infinity. Ln of 0 is negative infinity. That is the case, it tells you that your function on this designated interval, which represents your limits of integration, has an infinite discontinuity. So the evaluation of such a function will not be just like any ordinary integral anymore. It will require the steps of how to deal with improper integral. What is good about type 1 is you know right away it's improper because any of the limits are infinity, or both limits are infinity. The problem with type 2 is you don't know unless you first check. Okay, this is our first example here. I'd like to go back to the fourth because this is the one that I'm going to ask you. I'm gonna go tayo example for this one. The second of 0, this one, the second of 0. What's the second of 0? The cosine of 0 is 1. What's the reciprocal of 1? It's still 1. So meaning, if you substitute 0 for this, you will have an answer. Whereas if you substitute, what's the second of 90 degrees? The cosine of 90 degrees you said to me a while ago is 0. You invert that, that will be 1 over 0, and that's infinity already. So that tells you that this original function of yours on the designated interval, which is your limits of integration, will have an infinite discontinuity on the upper limit, which is pi over 2. That's the thing that we change here. So we change the value here. We change this particular pi over 2 to a particular, let's say, variable, which is x. It could be changed to any letter you want, but this pi over 2 was changed to x, and that's where your limit is going to approach to. Because in your original function, not on the integral of the function, if you substitute pi over 2, you will have an answer of infinity. So, ang infinity, hindi mo na mabutang sa curve. Class, kung mag-plot ikaw, basta infinity, it cannot be plotted anymore. So, your function is said to be discontinuous. It has an infinite discontinuity on the designated interval. So I hope you're getting this one. Why I need to come back to example, go back to example 4 and then from example 5, just to show you that an ordinary looking integral may be improper unless you check first by substituting the limits of integration on the original function. You won't be able, as I've said again, you won't be able to properly evaluate your improper integral if you just considered it as one ordinary definite integral, like this one. Okay? So this is our example 5. It shows to you that the that one of your limits of integration is approach from the right. Example 4 is approach from the left because of the sign that appears on your value in which your variable approaches, the limit in which your variable approaches to is negative or positive. So the third case under type 2 is this one. So both A and B has an infinite discontinuity. So this is what we're going to discuss after you take your break. So my time here is 3:44. Stop sharing. Okay, I'll go back to our slides. Okay, so we have type 2, case 1. Case 1 is when the upper limit is changed into a variable and it's being approached from the left. Okay. Case 2 is for the lower limit being changed and it's a variable that is being approached, or its value is being approached from the right side of the integral. This time, it's not any of the limits of integration itself wherein your function will have a discontinuity. This is even more difficult than the first two because this time, the infinite discontinuity is a value in between the lower and the upper limits. So this is improper integral of type 2 case C. Now what is this? If your function f has a discontinuity at C, where A is less than C and C less than B, and both the integral of the function evaluated from A to C and the integral of the function evaluated from C to B are convergent, then we define that the value of such an integral is equal to the sum of these two integrals, wherein the value C is in between the two original limits of integration. So C now is being used as the upper limit of the first integral and the lower limit of the second. If it's plotted class, it would look something like this. So just have this written in a smaller perspective. So you see here, your A is approaching C from the left because C is the upper limit. And your C here in the middle is approached from the right, starting from B because C is the lower limit. Okay, this C is the point of infinite discontinuity, where this line x equal to C is the line in which the left side and the right side of the graph of your function is going to be asymptotic to, tangential to, but it will never cross the set line. So they will just approach this line infinitely, going up. So this is the third case under type 2, or shall we say this is case 3. Why I say it's difficult? Because of this. So if we have this particular example, if you consider this as an ordinary integral class, look, I substitute 0 here on the original function. Your original function is 1 over x minus 1. If I substitute 0, the answer would be 1 over negative 1, and the answer is negative 1. If I substitute 3, the answer will be 1 over 2 because 3 minus 1 is 2. So you say, okay, this is an ordinary integral. But look, if you substitute a value of 1, which is in between 0 and 3 here, you will have division by 0. You will have 1 over 1 minus 1, and that's division by 0. So this integral should never be ever considered as an ordinary integral. This is an improper integral because in your interval or in the limits of your integration, there is a value wherein your curve will have an infinite discontinuity. So not in the lower limit, not in the upper limit, but somewhere in the interval, it will have an infinite discontinuity. And this is oftentimes where the error of most students will be seen, or could be, shall I say, be of use, because they fail to see that in between 0 and 3, you have 1, and it will make the graph of the function discontinuous. So this is improper. This is not an ordinary integral. So observe that the line x equal to 1 is a vertical asymptote of the given integral, or the integrand class is the function that follows after your integral sign. Okay, let's proceed. So since it is where the point of discontinuity, or since 1 is the point of discontinuity, then that would be the limit that we will assign, the upper limit that we will assign for our first integral, and the lower limit of the second integral. As you could see here, it is now the upper limit of the first, the lower limit of the second, and that's the C. This is actually taken from the property that the integral from A to B is equal to the sum of two integrals evaluated from A to C and from C to B. Okay, so you have same upper limit and lower limits for your two integrals here. Then you just go on evaluating the limits. So this will yield an ln. So you will have to replace the 1 here by the t, and you will have here 0. So we'll just processing this part here. We'll process this one here next. So we'll have the limit of the x minus 1. This should be class 1 minus x. Okay, another error here. So the limit of 1 over x minus 1. No. Okay, let me erase. If this is evaluated, this would be the limit of, there's some missing part here. I'll write it here, what's it supposed to be. This should be ln. The ln. The net wasn't able to write the ln. The ln of x minus 1. Because if this is integrated class, this will be ln of x minus 1. Your limits will be from 0 to t. So you see this one? 0 to t. After you have substituted 0 and t for the answer of your integral, which is the ln of x minus 1, you evaluate now the limit. So the limit would be evaluated as t approaches 1 from the left. Now, question, why do you know that it's from the left? Because it's the upper limit that you have replaced by 1. If it's the lower limit that you are replacing, then it would be approaching that particular value from the right. Take note of that. So if it's the upper limit, it's approached from the left side of the Cartesian plane. If it's the lower limit that was replaced, it's approached from the right. Okay, so we proceed. So you have here, after substituting t and 0, so this is when you substitute t first because it's the upper limit. So you have t minus 1. And then when you substitute 0, that would be 0 minus 1. And you have this. Okay? The ln of the absolute value of t minus 1 minus the ln of negative 1 because x is 0. Then we evaluate the limit of whatever is the resulting expression here as t approaches 1 from the left. Now, I have a question. Why do you think it came to this one? How did this ln of t minus 1 minus ln of negative 1 became like this, the ln of 1 minus t. Anyone? How did ln of t minus 1 minus ln of negative 1 became the ln of 1 minus t? This is something that was discussed to you in your EMA 101, in your differential calculus. How did it came to this? Are you there, class? How did it came to this? Anybody who knows how to simplify, how did it came to that? Drews Aujero, would you know how this ln of t minus 1 minus ln of negative 1 came to this? Or became ln of 1 minus t? Is Drews here? If you're there,
No, miss.
Drews Aujero, you're there? Oh, you're
Yes,
there.
miss.
Or would you know how ln of t minus 1 minus ln of negative 1 became ln of 1 minus t? At about Kyle Biko. Do you know? The reason why I'm yes.
Miss, I have no idea, miss. For I am assuming, miss, na you distribute the minus.
You distribute the minus? How can you distribute it? What about Kyle Biko? You have any idea? The reason why I'm asking you this is because this is already a past lesson. This is not something new. I'm just checking if you can still recall the properties of ln. Okay, this is it, class. Remember that whatever is taught to you, at some point in your higher subjects, you will be using them, especially with math subjects, because they are meant to be tools. Now, if your teacher asks you a question for a particular topic and it's not clear to you, you better ask question, because if the time arises or time comes that you will be asked for the application of that thing that was taught to you previously, you will really be lost because you can't understand, just like what's happening now. It is in the properties of ln that whenever you are dividing, it can be combined, or wherever you are subtracting rather, it can be combined into one ln. The argument of the first one is in the numerator, and the second one, which is subtracted, is in the denominator. It's the property of ln. So ln of t minus 1 over negative 1 could be written as ln of t minus 1 minus ln of negative 1. In the same way that if you have multiplication, it's addition of ln's. So if you have subtraction, it's division of the arguments. So if you have t minus 1 divided by negative 1, it's somehow correct with what was said before, that you are to take the negative of this. So you have the ln of 1 minus t, because you divided this by negative 1. So that would be 1 minus t. Okay, not that you distribute, as the term that was used, distribute the negative 1. But this is how you simplify the difference of two ln's. They can be combined as one ln, constituting of the expressions that were used in the subtraction. So the first one is in the numerator, written in the numerator. The second one is in the denominator. Okay, so since it's already the limit of ln 1 minus t here, if you will substitute 1 for the t in here, approach from the left side, you will have ln of 0. And again, ln of 0 is negative infinity as pointed out to you earlier. Okay, so it's negative infinity. Okay, this is because 1 minus t, the one you have here, approaches 0 as t approaches 1. So the value of this approaches 0 and the ln of 0 will be negative infinity when t approaches 1 from the left. Okay, so if you notice this first integral of the two, so I have only evaluated, so far we only have evaluated the first of the two. The first one has already a value of negative infinity. And since this is already non-existing, there's no point for us to process this one. Because any of this, if any of these two is non-existing already, that makes your integral for the two also non-existent. Or shall we say, the limit, or rather the answer for the said integral would be non-existing. So it is said to be, if you ask for convergence or divergence, then we say that the said improper integral is divergent. So whenever you have a case like this, for case 3, one already is divergent, there's no need for you to determine the other one. You get it? Any question? Okay, that's it. So this is in this case here. I'd like to go back on. They are to be convergent. Then we define that this is just equal to this. So if one is divergent, the other is it's not important anymore to evaluate the other because divergence of the one makes the answer of this original integral already divergent. Now we proceed. So it is divergent and we do not need to evaluate the second part. It's already divergent. Now we go to the next slide. So suppose we had not noticed, wala ta nakita, that the asymptote x equal to 1 in the previous example had, or we had that particular asymptote. And we just evaluated it as an ordinary integral. So what happens is, this would be our answer. If you did not notice that this is an improper integral, then you will just go on using your calculators for its evaluation. Your calculator will give you this. And this is not an acceptable answer because your answer should be divergent. Your integral is divergent, meaning its answer is non-existing. So you should not have actually in the first place an answer for this particular integral. So that's one. Actually, it takes practice not to forget that whenever you're given a definite integral, you are first going to check whether the limits, if they are substituted to the integrand, the function, will not have an infinite discontinuity on the limits, or if any of the values in between the limits will yield an infinite discontinuity for your integrand when plotted. So this is wrong because the integral is improper and must be calculated in terms of limits. So we don't evaluate improper integrals the way we do with ordinary integrals. They have to be converted into their equivalent expressions wherein we apply the concept of the limits. Now we proceed if there aren't any questions. Go to this one. So from now on, whenever you meet a symbol like this, you must decide by looking at the function on the interval a to b, whether it is neither an ordinary definite integral or an improper integral. So there's always a need for you to do the check. Now we go to example 7. Okay. This is still under type 2 because none of our limits of integration is infinite. Now, however, if you notice, look at here, you always need actually class to ask yourself, what would make my integrand, the function that is being integrated non-existing? So will have 2 in here, you will have 0. The square root of 0 is 0. 1 over 0 is infinite. So this tells you that this integral is improper because of the discontinuity of your particular integrand, the function in the integral, based on this lower limit. So sa lower limit siya. So this is actually case B under type 2. So first we note that the given integral is improper because for the function of x equal to 1 over the square root of x minus 2, you have the vertical asymptote x equal to 2. If you substitute 2 here for the x, you will have an infinite discontinuity for the graph of your function. As such, we say that the line x equal to 2 is the vertical asymptote. Okay, so I have mentioned that this should not be evaluated as an ordinary integral. So the infinite discontinuity occurs at the left end point of 2 and 5. So it's in the lower limit, and as such, this will be approached from the right. Lower limit naton ang iya discontinuity ara sa lower limit. So we use case 2b. Okay, case B. So the t that we replace the 2 in here is approached from the right side. So the value 2 is approached from the right side. So if we substitute before we substitute, we evaluate our integral using power rule. This would be this is actually x minus 2 raised to negative 1/2. So if you add 1 to the exponent, that would be positive 1/2 over 1/2. That is why you have this 2 square root of x minus 2 from t to 5. If you substitute 5 for the x, you will have 3. 5 minus 2, that will be square root of 3. And if it's the t, you will have the square root of t minus 2. This answer of yours for this integral that you have will be evaluated in terms of the limit as t approaches 2 from the right. So if you place 2 here, you will have square root of 0. So square root of 2 minus 2 is 0. So your answer would just be 2 square root of 3. So using case type 1 improper integral, case B, you will have 2 square root of 3. Or type 2 rather, type 2, because type 1 is you have the limits of integration as infinite. So this is type 2 case B. So the given improper integral is convergent. Convergent. Why? This is a real value. You get it? Any question? Still on type 2. Now we go to this one. So since the integrand is positive, we can interpret the value of the integral as the area of the shaded region. So this is the curve actually, class. The 1 over square root of x minus 2 curve. This is it. It starts from 2 and ends with 5. But these two value, the lower limit 2 is approached from the right. This is your upper limit 5 and this is your lower limit 2, which is being approached from the right side. So the area, the interpretation of such is the area of the curve is 2 square root of 3. The curve what? This is the curve. This is also what we call as the integrand. The function after the integral. Okay? Proceed. So a comparison test for improper integrals. What is this comparison test? So sometimes it is impossible to find the exact value of an improper integral, and yet it is important to know whether it is convergent or divergent. So let's say for example, you are having difficulty in determining the value of the integral itself, even if you have to apply the concept of the limit afterwards only. So what is this comparison test? So in such cases, the following theorem is useful. Although we state it for type 1 integrals, a similar theorem is true for type 2 integrals. So this particular theorem, which is useful, can be both applied to type 1 and type 2 integrals. So suppose you're given the function f and the function g, which are continuous functions, with f of x being greater or equal to g of x, where g of x is also greater or equal to 0, as long as x is having a value which is greater or equal to a. So if we're after the integral of the function from a to infinity, and it is said to be convergent, then we say that a to infinity of g of x is also convergent. When is this? When f of x is greater than g of x, as long as g of x will have a function which is real or greater than 0. It says here, the function of x is greater than g of x, which is greater or equal to 0 for any values of x equal or greater than a. For any values of x equal or greater than a. What does this particular x equal or greater than a represent? It represents the limits of your integration here. If it's equal to a, that's the lower limit. Greater than a, of course, this is the upper limit, infinity. Because it follows that if you have started with a as the lower limit, the next values to that will be values greater than a. So as long as this condition is followed for greater or equal to a value for x, and f of x greater than g of x, which is greater or equal to 0, if f of x is convergent, your g of x will also be convergent. Basta, amo ni siya ang condition na nag-apply. If g of x from the interval or of if the integral of g of x from a to infinity is divergent, then the function of x integral from a to infinity will also be divergent. If this g of x here integral as evaluated from a to infinity is divergent, then your function of x will also be divergent. We cannot change here convergence here to divergence. We can only use divergence for g of x. And it follows that g of x, your f of x will also be divergent. Now, in terms of graphical interpretation of this comparison theorem, ano na siya? Okay, we omit the proof of the theorem. It's not mathematical proof that is. So however, the figure makes it seem plausible. When we speak of plausible, class, acceptable, meaning it's acceptable. Your function of x, this is the one here, this is your curve, this is your g of x. So in terms of coverage, in terms of area, the function of x is really having a great bigger area than g of x. If the integrals of this function is evaluated from a to x, see here where x is approaching infinity, f of x is said to be convergent, g of x is also convergent rather. It says here. Okay, we go to the second term. If the curve under if the area under the top curve y equal to the function of x is finite, so is the area under the bottom curve, which is g of x. It's just an extension of what I've explained here. When you speak of finite, class specific, so kung ma-determine mo gini ang area ng function of x, where g of x is just a part of, it's common sense, si g of x is just a part of f of x because it's lesser than the area of the function of x, and it's bounded by the same boundaries as the function of x. So kung convergent si function of x, it follows, since g of x is just a part of it, g of x will also be convergent. What about this third one? If the area under your g of x is infinite, the area under this g of x is infinite, so is the area under your f of x. So if this g of x of yours in this particular boundary is infinite, since it's just a part of your function of x, then it follows that if this is divergent, your function of x will also be divergent. Why? Because this one is just a part of your function of x. So that explains these two concepts here. The important condition that you should not forget is this one. Function of x should be greater than g of x, which is greater or equal to 0 for all values of x equal or greater than a. This equal or greater than a is based on the limits. We started with a and end with infinity. These are your conditions for these two to be applicable to. Okay? Now, let's see in terms of application. Almost done, class, in terms of application. This is sample A. Show that your e raised to negative x squared dx is convergent on the limits 0 to infinity. Now, I'm sure for some of you who have done their practice integration in the indefinite integrals where if you don't still have the limits, you will know that this is a non-elementary integral. You have exhausted the resources that are available to you, you would have encountered a write-up or anything that tells you that this is a non-elementary integral. We can't evaluate the integral directly because it's non-elementary. And for undergraduate study, what is just covered is for elementary differential equations. Only elementary, meaning those that can be processed using your calculators and those that can be processed using the techniques that we covered. So the antiderivative of e raised to minus x squared is said to be is not an elementary function or a non-elementary function. The antiderivative meaning the answer to this given integral. Why is it not elementary or non-elementary? Because the integral itself is non-elementary. Okay, so then let's proceed. What do we do? So we write, so we're still on the application of the comparison theorem. We write 0 to 1 for the first limit of our integrand, e raised to minus x squared dx, and then we'll have 1 to infinity. So we applied here the property of integrals wherein from the original we can write two separate integrals having the same upper and lower limits. So you have this one now. We observe that the first integral on the right side, so this one, is just an ordinary definite integral. This one is referring to this. It's an ordinary definite integral. Why is that? Because it just substituted here, e raised to 0 and e raised to 1 squared. That would still be e raised to negative 1. Okay, for this one, the first integral on the right side. So this one here, we proceed. So in the second integral, we use the fact that for x greater or equal to 1, we have x squared greater or equal to x. Now, I would like to explain this further. Okay. It's referring for this integral class. We have 1 here, it's okay. But if it's greater than 1, it says here, we use the fact that for x greater or equal to 1, it follows that the square of that will also be greater than x. Meaning, if we substitute a value of x here, which is 2 or 3, of course it follows that the square of that would be greater than 1. Because if you square 1, that would simply be 1. But if you square 2, 3, and 4, that would be much higher than just 1 being squared. So this is the one that is being split here. So we say that negative x squared would be a lot less than negative x only. And therefore, e raised to negative x squared would be a lot lesser than e raised to negative x. We have this, of course, in your arithmetic, you will know that for a negative number, negative 1,000 is a lot lesser than negative 1. the bigger the numerical value of a negative number, the lesser is its value. Unlike when you say 1000 is greater than 1, because this one is positive. But when the number is numerically negative, its value, the value of that makes it even more and more lesser, more and more lesser, lesser and lesser and lesser. It's because of the negative sign here. More so, class, if you can try in your calculator, you write e raised to negative 1000 and compare it to e raised to negative 10. This one will be a lot lesser than this. This one is just purely comparing the x's, the x and the x squared, the pure value. But what more, if you are going to make this x squared and this x here both negative as an argument of the exponential function, this would even be lesser in value than this one. If they are plotted, I like to erase what I have written here. This is the curve of e raised to negative x squared. Let me check if I can make this video. Okay, this is e raised to negative x squared. This is what we call in differential equations. You'll be taking it up next year. This is exponential decay. There's a greater degree of reduction in the value of y because of this exponential function in which the argument is negative and it's being squared. So this is it. So kadako din sa ning panaog ya. Compare mo lang sa e raised to minus x lang, which is this one. Now, we haven't evaluated the limit. We just simply check the values of the function e raised to minus x squared and e raised to minus x and compare the two. So you can see that e raised to minus x squared eventually, as x approaches infinity, as it becomes bigger and bigger, will be a lot lesser than e raised to minus x. So how do we use this particular concept of comparing the graphs of the original function? The original function, which is e raised to minus x squared, which appears to be the integral here of our integral. So let's go to slide 56. So the integral of e raised to minus x is easy to evaluate. So if you're going to integrate e raised to minus x from 1 to infinity, that would be the limit of e raised to minus x from 1 to t. We change the t to infinity. Now you have the limit of, if you take the answer for this particular integral, this would be actually negative e raised to minus x dx. You need the negative here for this one, and you will have negative here. You need the negative 1 for the derivative of your u, eu du. So this negative here is the derivative of this one. Since I introduced the negative here, I need to place here negative. So the answer for this one is actually negative e raised to minus x. That's the answer. So the limit of e raised to negative 1 minus e raised to negative, wait class. Okay, negative x was changed to first, the t. Why is this negative 1? Let me check. So upper limit is t. This is your integral already. Wait lang. And then you have the limit of if you're going to apply the limit here to the answer of the integral already, you will have the limit of, I'll just first write the original, negative, I'll place the negative sign here, limit of e raised to minus x, and then you will have to substitute 1 and t in here. Okay? As t approaches infinity. There was an abrupt change of line here. Then I will substitute the limits here, class. So I will have negative limit of, I'll substitute e raised to negative t minus e raised to negative 1. So you will understand. So this is for t approaching infinity. And since you have the negative here, class, this will interchange the two. So you will have the limit of e raised to negative 1 minus e raised to negative t as t approaches infinity. Now, if you substitute class infinity here for e raised to minus t, hindi ko na lang sulat para makita niyo. E raised to minus infinity is equal to 0. It was discussed in the previous slide for this one. That makes this one equal to 0. That leaves you with e raised to negative 1. So that's the reason why you have here e raised to negative 1. Okay? Do you get it, or do you need me to process again? This is just the integral of the EU du, but oftentimes the student do not see that there's a need for negative 1 to be multiplied in here for the derivative of the u. Since you introduce negative 1 in here, you place negative 1 outside. So this integral actually will have this answer, negative e raised to minus negative x. Now, since this is limit, so I just copied it. I placed the negative sign before the limit. And this is the t approaching infinity in the limit. And this is your e raised to minus x. Ang negative niya, gimbutang ko na before sa limit para ma-follow nyo lang. You're not yet to evaluate the limit because you haven't yet substituted the limits here 1 to t, because the limit here is 1 to t for the integral that we evaluated. So you substitute it, first upper limit, next is lower limit. And since you have negative, it can be distributed here, or these two terms can be multiplied by negative 1, so that will interchange these two. You have e raised to minus 1 minus e raised to negative t as t approaches infinity. If t approaches infinity, you will have e raised to negative infinity, which is 0. So that is why you have this answer here. Okay? So that's the reason why you get to see this particular abrupt answer here and just a short line here of the solution for the limit. Before we go to the second to the last slide, do you follow the processing of this, the e raised to minus x integral? Are you still there? And I see a reaction, or are you already all asleep? Okay, you're still there. Thank you for those reactions. I hope you follow through. Okay, last page. Like to erase my markings. So the integral of e raised to minus x is easy to evaluate. So that's what we evaluated. Because remember, you have two integrals to evaluate. One which is non-elementary and the other one which is elementary. Okay, so then what happens? This is the last. So thus taking the function of x as e raised to minus x and the g of x as e raised to negative x squared in the theorem, we see that the integral from 1 to infinity of e raised to minus x squared dx is convergent. Why do we conclude in the first place that the integral of this non-elementary integral e raised to minus x squared from 1 to infinity is convergent? We used an alternative integral in the form of just the function e raised to x to evaluate, because hindi tanin siya ma-evaluate. Nangita kita sa mas simpleng integral nga ma-evaluate lang. Kay tungod ini siya, ang e raised to minus x is far greater in value than e raised to minus x squared. And based on the theorem that we have discussed, that if f of x is greater than g of x, which is greater than 0 for all x values greater or equal to a, then the said function is said to be convergent. So by comparison class, we concluded that this non-elementary integral is convergent without having to do any computation to the integral or evaluation to the integral of this. We use a different function, and that's the e raised to minus x. Ang question naman, base naman kung tumuti is nga aamo na siya ang gingamit. How? Babalik naman ta dire sa curve. Nga amo na siya ang gigamit because inkumpara diri nga kung ang ini nga curve na e raised to minus x squared is just a part of this curve which is e raised to minus x in terms of value because this one is exponentially decaying gamay value as x approaches infinity compared to e raised to minus x. So it's just said to be part of this one. And what are we using? What principle are we using for that? We go back to this one. Where is that particular function? This one. If g of x is convergent, and then f of x will be convergent. That is if the function of x is greater than g of x. The function of x is greater than g of x. Where is that particular theorem? Let me go back to that so you will find this one. The function of x is greater than g of x for x value greater or equal to e. So your g of x class actually is the e raised to minus x squared. Your function of x is the e raised to minus of x. E raised to minus x because in terms of plot it's greater than this one. And since we've learned that this one is convergent, automatically hindi siya convergent man. Idako pa yan si function of x kay g of x. We use this particular, shall I say, comparison theorem. We did not evaluate our original integral, but we use the comparison theorem to be able to answer a question whether it's convergent or divergent without having to evaluate its value. Why? It's impossible for you to have it determined because, as I've said, it's an non-elementary integral. This one is non-elementary. So you look for a function that you can evaluate in lieu of it, and that function is this, the e raised to minus x. Of course, this is already the HOTS. Have you heard of the HOTS? The V HOTS na gina siya. The part of the topic on improper integral which requires the very high order thinking skills. Higher order thinking skills na gina-require niya para ma-process ng estudyante. But nonetheless, I don't limit you to the non-higher or order of thinking skills because you are to be trained to think like those that have the HOTS. The College of Education would like to use it, the HOTS. Higher order thinking. And this one, under the topic of improper integral, will really let you think beyond what is being discussed, or you use the principles that were covered not only for now, but even past lessons that were discussed to you. Okay? This ends the topic of the definite integral and the improper integral. The reason why these two topics are always discussed one after another, the improper integral discussed after the definite integral, it's because of the fact that a lot of mistakes that are being committed by the students and evaluating integrals is that they would directly evaluate a definite integral, an integral with limits, as if it's just an ordinary integral. If they fail to check whether it's really improper, then the answer will of course be wrong. It's so easy to just give an answer because definite integrals are easy to evaluate because you have the students have their calculators to do that for them. mas budlay pa gani i-process ang indefinite kay wala sang answer. So ikaw gid ang masulat sang processes. Diriya ibutang mo na sa calculator mo maka-answer ka na dahil. So the common mistakes that's being committed by students is thinking of an improper integral as an ordinary integral, which is not. Type 1 is so easy because you see the infinite limits. Type 2 is where the error is always coming. Okay? Now, it's 4:45. I'll stop sharing.